Last lesson, we talked about converting alcohols to alkyl halides, alkylating amines, alkylating alpha carbons, halogenating alpha carbons, and forming esters with diazomethane. Today we are adding to our list of useful SN2 reactions. The first of our additions is called Williamson ether synthesis. We use an alkoxide as a nucleophile to form an ether. Pretty straightforward. However, alkoxides are also strong bases. We will always have competition with elimination, especially when the electrophile is secondary or tertiary. One way that we can help negate this is by making sure that the more substituted carbon chain is the alkoxide, which reduces the risk of elimination. We mentioned in the last chapter that an intramolecular reaction is possible, and often preferred when a 5 or 6 membered ring is formed. We can also form smaller rings. An epoxide is a particularly reactive ether ring and can be formed when the alcohol is adjacent to a leaving group, particularly if the alcohol is deprotonated by base, which essentially makes Williamson ether synthesis conditions. Ethers can also be formed in acids. An acid makes the alcohol oxygen a better leaving group. Since there's more alcohol that's still present, an alcohol can be a nucleophile in a substitution, either by SN1 or by SN2. It kicks out the water, and the resulting ether has an identical chain of carbons on both sides of the oxygen. In theory, we could create an asymmetrical ether using this process. However, we'd also make every other possible product, so this really only works for symmetrical ethers. Ethers normally aren't particularly reactive because the product would be no more stable than the reactant, and the transition state is fairly high in energy. However, substantial ring strain makes oxyranes, also called epoxides, much more reactive, and they can react under pretty much any conditions, even with weak nucleophiles. The first elementary step in these cases is the rate limiting step. But now, even though the leaving group is poorly stabilized, the ring opening makes the product more stable than the reactant and allows the epoxide ether to react in basic or neutral conditions. There are tons of different nucleophiles that can open an epoxide, and the really cool thing, one bond is formed and you get an alcohol functional group on the same product. The examples shown are all examples of carbon-carbon bond formation with epoxides. Alkyl lithiums on top, Grignard reagents, and sp hybridized cyanide or terminal alkynes all can serve as nucleophiles, all of which are under basic conditions. We need to give special consideration to asymmetrical epoxides because the side that the nucleophile attacks will determine which product is formed and will make the product stereospecific. Under basic or neutral conditions, both of the epoxide carbons are similarly active, but the nucleophile will react with the less sterically hindered carbon and give the alcohol on the more substituted carbon. So we know that we will get one specific product if we react in base, but what if we want the other one? Here's an example of the exact opposite selectivity which occurs in acid. When we react with HBr, we end up with the alcohol on the less substituted carbon, the opposite of the regioselectivity that's in base, and the nucleophiles on the other side. This can be explained if we think of the order in which the elementary steps take place. In base, the first step is the bimolecular substitution, and a proton transfer comes after the regioselective reaction has occurred, so the product has already been determined at the first step. In acid, the first step is a proton transfer, which will change the reactivity of the epoxide carbons. The extra positive charge on the epoxide oxygen weakens the carbon-oxygen bonds, but it does so preferentially to put the more positive charge on the more substituted carbon, because the more substituted carbon can better stabilize it. This means that the more substituted carbon is more electrophilic, and the reaction will be directed there. Oxetanes, which are like oxyranes, epoxides that is, but are lower energy, can react somewhat similarly. But let's think about how the reaction energy coordinate diagram changes between these two. We know that ring opening releases a lot of strain energy, so our reaction is exergonic, like this, right? So what happens to the energy of reactants if we have lots of strain? We should see an increase in reactant energy, making the reaction more exergonic. On the other hand, if we release some of the strain, like having a bigger ring to have less ring strain, we'd have lower energy reactants and a less exergonic reaction. For this reason, oxetanes, the four-membered cyclic ethers, only react if we have very strong nucleophiles, but otherwise are not very reactive. If we have a larger cyclic ether like a tetrahydrofuran, a five-membered cyclic ether, the molecule becomes even more stable and we consider it unreactive. Epoxides aren't the only three-membered cycles formed through an SN2 intramolecular reaction. The cancer drug mechlorethamine will form a three-membered nitrogen ring called an aziridinium ring through an intramolecular SN2 reaction similar to the formation of an epoxide. This aziridinium is now both strained and has a good leaving group and can easily alkylate DNA. Since the reaction can happen on both sides of the molecule, mechlorethamine will link strands of DNA together, which prevents replication. Obviously, no replication is a good thing for cancer cells, but like many cancer drugs, it is pretty bad for replicating cells, other replicating cells. Nothing makes this more obvious than a brand name for mechlorethamine, Mustergen, which identifies this compound's use in chemical warfare and its relationship to the similarly reactive mustard gas shown at the bottom of the slide. We've mostly talked about particularly useful applications of SN2 reactions so far, but there are also some interesting elimination reactions. Of particular importance is the elimination of a leaving group on an alkene to form an alkyne. While these reactions do occur, they definitely don't occur by E1 conditions because the vinylic carbon leaving group bonds are quite strong. Functionally, this means we need a strong base and some additional heat. The reaction shown here has the hydrogen anti-paraplanar from the leaving group, which is a requirement for E2 reaction mechanisms. However, this reaction does not have that requirement, suggesting this reaction doesn't occur strictly via an E2 mechanism either. The mechanism is not well understood. Here's a straightforward example of this reaction. A strong base removes the only acidic proton on the molecule at the same time as the leaving group leaves. We get one product in high yields. We can actually get different products in many cases depending on the strong base that we use. Using a sodium amide base for this reaction, we end up with a 1-pentyne, the product that we'd expect from a simple elimination. If we use sodium hydroxide instead, we end up with a more thermodynamically stable disubstituted alkyne. The first is irreversible and is under kinetic control. The second is reversible and is under thermodynamic control. Let's talk about the reversible reaction first. The first reaction is an elimination to an alkyne, forming the terminal alkyne. Because the sodium amide is a very strong base, it can actually deprotonate the acidic alkyne proton. Proton transfers are fast, and the resulting product will not further deprotonate. It is stuck as a terminal alkyne until the reaction is worked up in acid. A reaction workup is often a neutralization and an extraction into an organic layer to remove all the aqueous components, in this case, ammonium and any sodium bromide salts. The reversible reaction is a little more complicated, but starts with the same first step. Because hydroxide is a weaker base, it can't deprotonate the alkyne proton. However, the protons alpha to the alkyne have a slightly increased acidity due to resonance. Hydroxide can pull off this alpha proton and put it back with any water that's in solution. You can pull it off, you can put it back and forth, and so on. But it can also pull the proton back in the other negatively charged position in the resonance hybrid. The resulting isomer can go through an identical process to take off another proton on the same position and eventually put it again on the other side, resulting in the alkyne moving from a terminal position to a more stabilized position. All of these reactions are in equilibrium. The only reason that we end up with a product isomer is that it is more stable than the terminal alkyne, and so eventually, since all of these things can go back and forth, the equilibria will all gradually dump to this more stable isomer. Of course, we don't always start with a vinyl halide. In order to get a vinyl halide, we often start with two halides on a starting molecule. These halides may be on adjacent carbons or on the same carbon. It doesn't really matter because the first elimination will make a vinyl halide in both cases. Even if the halides are on adjacent carbons in a molecule that could give multiple elimination products, the inductive effect from the halogen makes the hydrogens attached more acidic, and the vinyl halide will form preferentially to the allylic halide. The allylic halide being where the halide is one carbon away from the alkene rather than directly bound. The other really interesting application of elimination reactions is a Hofmann elimination. In this elimination, we alkylate an amine like crazy until it is an ammonium. The positive charge on the nitrogen makes it a good leaving group, and if there is any base in the reaction, we can eliminate the nitrogen as a neutral amine. Even though usually the more substituted alkene, the Zaitsev product, is formed by elimination, the product formed in this case is anti-Zaitsev, specifically the less substituted carbon. This makes sense when you consider the size of the amine leaving group. Sterics are so significant that they prevent base access to the more substituted position, and the less stable alkene will form because the protons that need to be removed from it are more accessible. This makes even more sense when you think about conformations. Remember that an elimination by an E2 mechanism requires anti-periplanar conformation. On the less stable side, this requires a Gaussian interaction between a carbon chain and a trimethylamine. However, on the other side, we're going to have access to an anti-periplanar hydrogen in the most stable conformation, and so the E2 reaction can happen much more readily. Chapter 10 begins in earnest our study of synthetically useful reactions. The mechanistic considerations for all of these are rooted in the discussions that we had in the last chapters, but we still need to do some memorization of the reagents that we use and what type of mechanistic considerations we need to make. So at the end of this chapter, we'll review the specific reactions that we talked about. We can convert alcohols to halides using PBr3 and PCl3, but only on primary and secondary alkyl halides, because it's an SN2 mechanism. We can alkylate ammonia and amines, but it's really hard to stop, so it's most useful for making quaternary amines. We also can form carbon nucleophiles by taking advantage of acidity at the alpha position to a carbonyl, particularly of an aldehyde or ketone. By taking advantage of the tautomerization reaction, we can have a nucleophile for the halogenation even under acidic conditions. Remember, this was preferred because it allows for a single halogenation. Diazomethane provides for a special reaction converting a carboxylic acid to an ester because of the strength of nitrogen gas as a leaving group. We can take advantage of alkoxide nucleophilicity to make ethers, but we need to be careful to avoid eliminations. We can also use this nucleophilicity to make a strained ring ether, which can then be used to react via SN2 reaction at any acidity because of the ring strength. Remember, those are called epoxides. We talked about the formation of alkynes using the elimination of vinyl halides, and also about the Hofmann elimination of an amine that gives the opposite product to most other eliminations. The tables 10.1 and 10.2 at the end of this chapter in your text give a summary of these reactions. It is really important to pay attention to these summaries, but also to recognize the specific products that are formed in each case often are going to require an understanding of the mechanism rather than just rote memorization.